So the relativistic mass-energy relationship will feature prominently in our attempt to generalize quantum mechanics to a relativistic setting. So let us take this opportunity to review the relativistic mass-energy relationship. So we start with the relationship between proper time and time in a inertial frame, and in that inertial frame, v is the speed of the particle in question. It's the instantaneous speed, and c is the speed of light. Then the generalization of the idea of momentum to a four-dimensional momentum called four momentum is p mu mass times the four velocity, which is dx mu by d tau. Now, if you remember, this is c times dt by d tau, and then we have m times d, the spatial coordinate dxi with respect to d tau. So let's look at the zeroth component of the four momentum. The zeroth component is given by mc dt by d tau. Now, using this relationship, the relationship between proper time and time, we can write this as mc divided by 1 minus v squared by c squared square root. Now, in the non-relativistic limit, where v squared by c squared is much, much less than 1, we can expand p0 in powers of v squared over c squared, and then this will become mc1 plus half v squared by c squared and higher order terms. So this becomes mc plus half m v squared by c. Now the second term should ring a bell. This is nothing but the kinetic energy in the non-relativistic particle divided by the speed of light, and therefore, c times p0 is going to be mc squared plus half mv squared. So this is a kinetic energy, but what is this? And see that at the limit where v goes to 0, the kinetic energy goes to 0, but the first leading term doesn't go to 0. So this is basically, if you call this the energy of the particle, then we can say that in relativistic setting, the energy of a free particle has a part which is could be associated with the mass of the particle, and it only depends on the mass of the particle. It doesn't depend on what its speed is. And then there are higher order corrections like that. So this is basically where the famous formula E equals to mc squared comes from. So now with this definition of E, we can now write P mu, the four momentum. The zeroth component of the four momentum is then E divided by C. And then the other component are P1, 2, 3. Now, P mu is an example of a contravariant vector. And then P downstairs mu is an example of a covariant vector. Then P upstairs mu, P downstairs mu is a Lorentz scalar, meaning that it does not change under Lorentz transformation. So we shall write Lorentz combination of two Lorentz vectors in this way. So this is p squared. So this has to be invariant on a Lorentz transformation. But by dimensional analysis, the only thing that it can be proportional equal to is m squared c squared, because these are momentum. So the square of the momentum must have dimension of square of momentum, and mc has the dimension of momentum. So because of this, what is p squared? P squared is, of course, e squared by c squared, and then the 3 momentum p whole squared equal to m squared c squared. And therefore, we can rewrite this as energy squared is equal to p squared. I'm just dropping the the modulus signs, plus m squared c to the power 4. And therefore, the relativistic mass-energy relationship is E is equal to the positive square root of the 3 momentum squared c squared plus mass squared c to the power 4. So this is the famous relativistic mass-energy relationship. So just note that the relativistic mass-energy relationship implies that when the particle is at rest, that is when P is 0, the energy of the particle is given by mc squared.